All right. So for most of today, we're going to be covering the last unit, which is I forget how it's termed in Canvas, but the stuff that's only going to be on the final exam will be most of what we cover today. And then the next class that'll be true as well. The very last day of class, 1 week from today, as we talked about, is going to be a sort of a hodgepodge of review topics, and a little bit that will sort of assess teamwork, which we're required to do in this class. So you do need to be here in person if you want to earn that 1% of your grade on the very last day of class. All right, so we're going to start with today, though, before we get into the newest stuff, are just three more example problems that we left off with last time on phase diagrams. So this would be the last topic for exam 3, as a reminder. So we're just talking about how to read phase diagrams and then different things that we can sort of interpret from them. So in this one here, most of the previous problems, or all of them, I think, dealt with sort of a static situation. You're at a specific point on the phase diagram and asking some question about what phases are present or what the phase change temperature would be and stuff like that. Here we're talking about actually moving through a phase diagram, so it's a little bit more involved. So we're starting with the substance at 0.2 atmospheres, 100 Kelvin. Then we increase the pressure to 2 atmospheres while maintaining a constant temperature. And then which of the following lists the phases that will be encountered during this process? So for problems like these, it's really just about reading the graph. So if we're starting at 0.2 atmospheres and 100 Kelvin, we're going to be right here. And as you recall, a good starting point for any problem that involves phase diagrams is to remind yourself what the three different sections mean. So solid on the left, liquid in the middle, gas on the right. So we're starting out here in the part of the diagram that's in the gas phase, and then we're going to increase the pressure to 2 atmospheres. So we're going to go all the way up in pressure. Pressure is the vertical direction, so we're staying at the same temperature, but going up in pressure until we stop there, and we've reached the middle part of the diagram, which is liquid. So this process is going to be starting in the gas phase. Now, as we go through, though, to get to the liquid phase, which is where we end up, when we cross over here, we're going to be crossing over into the solid phase. So once we reach about 0.4 atmospheres, you'll encounter the solid phase until we get up to here at about 1.6 atmospheres. We'll cross to the liquid. So actually, in this process here, we've encountered all three phases, and that's the order we go in. So we start in the gas phase, we cross over into the solid phase as we're raising the pressure, and then at even higher pressures above 1.6, we convert into a liquid. So the correct answer would be choice D here. Now, choice D is the only one that has the correct starting point, so I guess we could have probably eliminated all the rest if we just recognized where we were at the beginning, but that would be the correct order. Gas, then solid, then liquid as we go up in pressure at a constant temperature of 100 Kelvin. Okay. And then the next one deals with the densities of the solid and liquid phases. So as you recall, we talked about how the slope of the line that divides those two, solid, liquid, gas, this is the line that divides solid and liquid. The slope of that line is going to determine which of those phases is more dense. Now, as you recall, if you want to remember it, you could just sort of memorize the two possibilities. But what you can think about is if you start here close to that borderline, but we're in the solid phase, if we increase the pressure, and we saw this in the last problem too, if you increase the pressure at a constant temperature, you go from solid to liquid. And recall that when you increase in the pressure, you're compacting the substance, so it's making it more dense. So as the substance becomes more dense, it converts from a solid to a liquid, telling us that the liquid is the more dense phase. All right, so that's going to be choice B here. You won't really ever see the slopes of these lines, other two lines, varying because the gas phase is always going to be the least dense for reasons we talked about in chapter 8. The molecules are spread far apart, not in contact with each other anymore. So your gas phase is always the least dense phase. So you're going to have a positive slope for the sublimation line, positive slope for the vaporization line. But this line here that divides solid and liquids, for most substances, it's actually the opposite. But for some cases, like water or like this fictitious substance here, the liquid is more dense than the solid. That's certainly possible. All right, and then the very last one is asking about vapor pressure. What is the vapor pressure of this substance at 250 Kelvin? So we can read vapor pressure off of these diagrams by recognizing that that's going to be the pressure at which the liquid and the gas phases interconvert at a given temperature. It would be the boiling point at that temperature as well, or at that pressure as well. So if we're at 250 Kelvin here, we want to figure out what's the vapor pressure. We just go up to where that liquid gas line crosses. So we're at that point there. We extrapolate over to the y-axis. It's a little bit above 1.2 atmospheres. We have to estimate a little bit, but we would say that the vapor pressure at that temperature is around 1.25 atmospheres, which tells us that we're above the normal boiling point, which we considered in a previous problem. But again, if you just read off this liquid gas line here at any temperature, that's going to tell you what the vapor pressure of the liquid is at that specific temperature. And that's exactly what we did here. All right, so any questions on those three problems or phase diagrams before we wrap that up? Okay, so the last few sections of the entire course then in chapter 9 deal with the solid phase, the one phase that we haven't talked a lot about yet. And mostly what we're going to be doing for solid phase substances, we're going to be talking a lot about their structure. So how do the atoms or molecules line up in the solid phase, and how do they organize themselves to make these rigid solids? And then also a bit about the properties of them as well. So before we get into details about structure, let's talk about the different types of solids that we can have. There's really two major classifications. So the first one are called amorphous solids, and these are going to be solids that have no regular structure. Whatever atoms or molecules make them up are just sort of randomly organized. So depending on what kind of substance it is, it's going to be made up of either atoms or molecules or maybe ions if it's an ionic compound. But whatever makes up that substance is just going to be arranged randomly. There's no regular pattern or regular order to it. All right, they're still solid because those atoms and molecules are largely fixed in place. They're not moving around each other anymore, but there's not a regular pattern to it that we can easily define. There's really only one classic example of an amorphous solid that you need to be aware of, and we're not going to say really much about these because, again, if they're amorphous, you can't really say anything about the structure, so it's kind of an unsatisfying class of materials to introduce in a course like this. So really, you should just be aware that the classic example of an amorphous solid is glass. So glass, there's different types of glass, but most of it is SiO2. Most of the substance is SiO2, silicon dioxide. But the silicon and oxygen atoms that make that up, there's no regular pattern to them. They're kind of just all randomly interconnected with each other in a and there's no way to really clearly define the structure. The type that we will talk a lot about in this part of the course are called crystalline solids, and these are ones where the components, the atoms, molecules, or ions that make them up, are highly organized. So they're arranged in a highly regular and periodic fashion. So by periodic fashion, it means that whatever small unit you have is going to repeat continuously, typically in all directions. There can be different dimensionality, but you would have certain atoms or ions arranged at a specific distance from each other, and then that unit is going to repeat in all directions over and over and over and over again. So the lattice would be the three-dimensional system of points that then comprises the crystalline solid. Where each point represents an atom or a molecule, if we're talking about it in a chemistry context. So a lattice is basically a system of points that repeats in all directions. A three-dimensional lattice would be one that repeats in all directions. And in a chemical compound, in a crystalline solid, those points would be the atoms or the molecules that make up that substance. Now, as maybe a more relevant, or I guess easier to visualize example of a lattice, this has nothing to do with chemistry, and it's a two-dimensional lattice, but nonetheless, I guess you could, in some way, you could consider this tile floor to be a lattice. It has those crisscrossing lines that go on. If the floor went on forever, would go in all directions, just in 2 dimensions. Or this is more of a thing that was more common back when I was your age, less so now. But if you have patterned carpet, if you've ever been to like an airport or a hotel that has like patterned carpet and it's the same pattern that repeats over and over and over again, that would be a 2-dimensional lattice. It's just a series of points or objects that repeat regularly in all directions. Typically in chemistry, at least in this course, we're going to be talking about 3-dimensional systems where it goes in all directions, but it's a repeating pattern. So how we define a lattice then is in terms of what's called the unit cell. So the lattice is the smallest repeating unit that we would have. Now, perhaps that's not the most precise definition, because what a unit cell really refers to is the piece of that lattice where you can generate the entire lattice by just translating the unit cell in all directions. Now, there's going to be a pretty simple way to visualize what's happening here. Um, because most of the unit cells we're going to talk about in this course, there are many other varieties that you won't get to here in general chemistry, but you'll learn later on if you continue in chemistry. But most of the unit cells we're going to talk about are cubic in shape. They're just a cube that has atoms or ions arranged around the different parts of the cube. And then the lattice would be generated by taking that cube and stacking it in all directions. Imagine you're taking cube-shaped blocks and you're just stacking them all on top of each other, keep going higher and higher and higher, keep going further and further out. The lattice would be that whole array of blocks, and each individual block would be the unit cell. Okay, so that's how we sort of generate these crystalline solids. We take a little repeating piece and we stack it in all directions. So we're going to really define things in terms of what the unit cell would be. Now, within crystalline solids, there's a few different subcategories that will come up. So one is called an atomic solid, and really the types of crystalline solids are defined in terms of what kind of substance they comprise. So if you have an atomic solid, as the name suggests, that means the lattice points are only made up of a single type of atom. So the whole lattice is just one element, one type of atom that repeats in all directions. So a lot of the solid state elements and elements that are solids in their standard state or in other conditions would be classified as atomic crystalline solids. So the example that's pictured above is diamond. So one of the forms of carbon is a crystalline atomic solid where each point is a carbon atom. And they make these tetrahedral arrangements. We'll talk more about the structure of diamond later on. And then most metals on the periodic table. So we talked about the standard states of elements, and pretty much every metal except for mercury is a solid under standard conditions, and most of them are also crystalline solids. They would be classified as atomic solids, just a single type of atom in that whole structure. Another type that we'll talk a lot about, but not until next time, are ionic solids. So most ionic compounds can form crystalline phases that have repeating arrays of positive and negative ions. So now there's two different types in the structure. So the ones that we'll talk about a lot in this class and so pretty much any ionic compound would fall in this category, but you would have sodium chloride was one we'll talk about. Zinc sulfide has a distinct structure. Magnesium chloride. Any ionic compound, any binary ionic compound especially, would fall into this category. And then the last type, which we won't talk about as much, but we should be at least familiar with at a basic level, are called molecular solids. So molecular solids are covalent compounds that exist in a crystalline solid phase. So in this case, the lattice points are the molecules. And those molecules would be held together by intermolecular forces. In the other two categories, you have actual chemical bonds holding all the atoms together. So in diamond, it would be covalent bonds. In metals, it would be what's called a metallic bond, which we're going to talk about here in a second. And in ionic compounds, it would be ionic bonds. In molecular solids, you just have the bonds within the individual molecules, and then those molecules will be held together by intermolecular forces. So the example which is pictured here is ice. And if you've ever seen a snowflake, I know we don't see them very often in Houston, but they often have these sort of nice hexagonal shapes to them and patterns, and that's because of the crystalline arrangement of the water molecules in these regular, often hexagonal patterns as is shown here. Okay, so those are the types of crystalline solids. We're going to mostly talk about metallic solids and ionic solids. We'll give a little bit of information about the other ones, the non-metal atomic solids, as well as some other types. But again, those metals and ionic compounds are going to be the big focus for us. So to understand metallic solids, the first thing we need to understand is what's called metallic bonding. How are the metal atoms held together in a crystal like this? Because the individual metal atoms are overall charge neutral, so there's not going to be ionic forces holding them together. But what there actually are there's actually bonds between the metals that involve sharing their valence electrons. So one way we can think about this is let's just consider the simple example of a group 1A and a group 2A metal. So group 1A is that first column in the periodic table. And so what we know from group 1A and what we learned a long time ago is that they all have one valence electron. They have an s valence electron, 2s, 3s, 4s, depending on what row of the periodic table you're in. And that outer valence electron is held pretty loosely. That's what gives it the ability to form ionic compounds pretty easily, because it can give up that one electron relatively easily. They have low ionization energies, is another way to think about that. So if you have a group 1A metal, what you basically have is one loosely held valence electron. And the way that those metals then bond to each other is those loosely held outer electrons are kind of just floating around and holding all the atoms together. So you can kind of visualize it as an array of positive charges plus one charge if it's group 1A, because they have one valence electron. And then those electrons are not lost in this case, but they're going to be floating around and holding the whole thing together. So I'll draw just sort of a yellow smear here over the whole structure that represents the valence electrons just holding those atoms in place. The valence electrons are now delocalized. They don't belong to one atom or another. They're not just shared between two atoms. They're just delocalized over the entire collection. They're freely moving around. So in these diagrams here, this yellow that I'm drawing as a sort of a ill-defined smear is what we call the sea of electrons. So it's loosely held valence electrons that are just freely moving through the entire structure. So in these metal solids, your valence electrons are typically loosely held. And delocalized. And those valence electrons are responsible then for keeping the metal atoms organized into those regular crystalline structures. So if you go to group 2A, you would sort of visualize it very similarly, except in group 2A, we have now two valence electrons. They're all the S2 configurations for their valence shell. So you would have two loosely held electrons. So you would have basically 2+ cations now, not formally cations, but the core electrons would form sort of a 2+ charged unit, and the valence electrons would be floating around those, holding them all together. And this time you'd have twice as many delocalized electrons because you have two valence electrons to consider. All right. So very similar pictures with different numbers of valence electrons, but the idea that the electrons in these metallic solids are not confined in one specific location, but are delocalized over all the atoms and responsible for holding them together in those arrays. So then what we should think about are what are some of the properties of metals that relate to this form of bonding? So a key part of chemistry as a whole, and which we'll touch on in this chapter, is relating the structure of a material and its bonding to its properties. And so if you think about what are some of the properties of metals and how do they depend on this arrangement of their electrons, the first thing we can talk about are the melting points of metals. And they tend to be moderate to high. Because you have this sea of electrons holding everything together. And so if you want to break those atoms apart into a liquid, you have to break some of those interactions. We can make some predictions about how the melting point would increase or decrease as we move through the periodic table based on this model here. So if we move across a period, meaning we're going left to right across the periodic table, what you would tend to see is that, especially for the main group metals, but it holds largely true for transition metals as well, the melting point increases. Because as we talked about, as you move from left to right, especially in group 1 and group 2, where it's very obvious, you have more valence electrons that are in that electron sea. So that correlates then with stronger attractions between the metal atoms. All right, the picture we just drew, group 1A has 1 valence electron per atom, so you'd have that many electrons sort of floating around holding everything together. Group 2A now has 2 valence electrons per atom, so there's twice as many electrons that are holding the atoms in place, meaning it's going to require a higher temperature to separate those atoms and make it into the liquid phase. As we go down a group, so that's going top to bottom, for example, in group 1A, lithium down to sodium, potassium, rubidium, and cesium, as we go down a group, the melting point goes in the opposite direction. It's going to end up decreasing. And this relates to things we learned also back in chapter 2, recognizing that as you move down a group, the valence electrons get further and further away from the nucleus. So we go from 2s to 3s to 4s to 5s to 6s as you go down that first column. And that means that because they're larger and the electrons are held less tightly, then you have a weaker attraction of those ions to the electron sea. Just because they're larger ions, everything's more diffuse, everything's less tightly held together when they're spread further apart. All right, so whether you fully understand the reasoning or not, basically, as you go down a periodic column of the periodic table, you would expect the melting points of the metals to get lower and lower. So as you go down group 1A, cesium is still a solid at room temperature, but it's kind of a soft, waxy solid, pretty easy. It has a pretty low melting point compared to lithium up at the top. Now, if we talk about the boiling points of metals, which we don't usually discuss, we don't think about boiling metals too often, and that's partly because they have very high boiling points. Because if you want to liquefy a metal, you don't really have to break all the metallic bonds. You have to reorganize the atoms and get them sort of flowing around each other. So that requires some energy, but you're still, the electron sea is still largely holding the atoms together. But if you want to boil them, you have to completely separate the atoms, break that entire network of electrons that's holding it together. So it's very difficult to do that because of the nature of metallic bonding. You have to actually break the metallic bonds, and it's difficult for those formal cations at the center and their valence electrons to break away from the others. All right, there's a lot of forces of attraction between the valence electrons and the metal atoms that are held together. You have to break all of those to boil it, so these tend to have high boiling points. Just like we talked about at the beginning of this chapter, when you're considering the temperature or the amount of energy that's required to do a phase change, it really is a function of how strong are the forces that are holding the atoms and molecules together. Metallic bonding is reasonably strong, so it requires a decent amount of energy to melt the substance and a much higher amount of energy to boil the substance. Now, there are some other classic key properties of metals that originate from the electron sea. So when you think about a metal, you probably have some idea of how they behave if you've ever dealt with them in your real life. So one is what's called the mechanical properties. Basically, mechanical properties of any substance is what happens when you put a large force onto that substance. And is it really strong? Is it really weak? Does it crumble? Does it stay together? Different possibilities. In terms of their mechanical properties, metals are fairly unique because they are what we call malleable, meaning that they're able to be bent and molded pretty easily, even without melting them. You guys, for example, a paper clip, right? You can bend a paper clip and it doesn't just snap in half very easily. Of course, it can, but you can bend it pretty well without it completely snapping in half. And that's because in this electron C model, the metal ions are held together. There's strong contacts between them, but there's a bit of flexibility. They're not tightly held in a single location because, again, there's a sort of diffuse cloud of electrons holding it together. And so these atoms can sort of slide through the electron sea and move around a little bit. It's difficult to completely break them apart. That's why we said it's difficult to melt the substances. But because of the diffuse nature of the bonding, because you don't just have two electrons holding two atoms together, but rather floating around the whole structure, you can kind of move things around without disrupting that too much. They're able to be bent and reshaped pretty easily. In terms of another important and obvious property of metals is that they conduct electricity and heat very well. Most of the conductive substances that we use in wiring or in devices are made up of metals. And that's because they have those loosely held valence electrons that can easily travel through the whole structure. And so this is especially obvious for electrical conductivity, where it's the actual electrons that are moving, because you have this sea of loosely held electrons that can freely move around. That leads to the ability for them to conduct charge very readily. So in their solid or liquid state, where you have these sea of electrons holding everything together, the electrons are mobile, so that allows the charges to be conducted very easily. All right. So that's a bit about metallic bonding and some of the properties that result from it. Any quick questions on that? All right. Probably the more the part of this that you're gonna have to spend a little bit more time on, I suppose, or that's going to be a little bit more involved and in detail, is going to be the structures of crystalline solids. And we're going to start with metals. That's what we're going to cover today. We'll do ionic compounds next time. But how do we define the structures? What are the different possibilities that we have? So the first thing I want to do is, this is probably not going to be something you'll be tested on, but I want to give you a little bit of background on how do we determine these structures. So I'm going to give you a lot of information about the arrangement of atoms in different metals, the shapes that they make up, the distances between the atoms, all this different information you can have to define the structure. And in reality, how do we know what that is? How is that experimentally determined? So that was done primarily by a technique called X-ray diffraction. So if you've ever done a diffraction experiment in physics, if you shine light through an array of slits or points that are regularly spaced apart, the light will start scattering in different directions. And that's exactly what can happen with X-rays when you shine them onto a crystalline substance. Because in a crystalline substance, you have atoms or molecules that are repeating units that are in regularly spaced arrays. And so the X-rays will diffract off of them and bend in different directions. So that's sort of the key of this experiment. The X-rays will scatter off of atoms that are arranged in crystals. So then when these X-rays scatter, you're going to get some regions where the scattered X-ray beams are in phase with each other, and you're going to get constructive interference between those scattered beams. And then you're going to get some regions where the X-rays that are scattered off are going to be out of phase with each other. You'll get destructive interference, and those waves will essentially cancel out, and you'll lose intensity there. So then what you do the experiment, what you'll end up seeing is that you'll shine your X-ray beam onto the crystal that's shown here. You're going to get X-ray beams diffracting off of the crystal, and in the place, and then you would have a photographic plate or a detector that those scatter beams are going to go to. That's usually about 5 to 10 centimeters away from the crystal. And then where you have constructive interference, you're going to see spots that represent higher X-ray intensity at those positions. So the spots on the detector plate, they used to use photographic plates for this that were basically just like photographic film. Now we have detectors that you don't have to replace all the time. So the spots on the plate represent where the X-rays constructively interfere. So then basically what you do is you have this pattern of spots on the plate. You also rotate the crystal in all directions and measure that same pattern of spots for other orientations of the crystal relative to the X-ray beam. All that gets put together with a lot of math that we're going to barely cover in this class to then tell you what is the arrangement of the atoms that gave rise to that specific diffraction pattern. Um, and again, the math is very complicated and involved. So in the old days when they first started doing this, and you had to do the math by hand, it would take several years to piece one of these structures together. Now everything's computerized, and in an ideal situation, we can do it in like 20 minutes. It takes usually a few hours to collect the data, but then analyzing the data takes like 20 minutes or so. We do it all the time now routinely. But it's a lot of math that goes into it. We're going to sort of cover just the very basics of that math here in what is called Bragg's law. Bragg's law has a cool origin story because it's named after two scientists, both with the last name Bragg. So a father and son combination that came up with this together and won the Nobel Prize for it. So I think back when I was a kid playing baseball with my dad, and some people were winning Nobel Prizes with their dad. So quite a bit different upbringing for these Bragg people, but they made a very important discovery nonetheless on how we can analyze the diffraction pattern of X-rays and piece that together and relate it then to the way the atoms are arranged in the crystal. So in this model here, what you have is to consider are a few parameters. So you have lambda, which is the wavelength of the X-rays that you're using. And that's going to be dependent on how you generate the X-rays. That's a known quantity. And then, as we said, you're going to have X-rays going into the crystal, diffracting off the crystal, and there's going to be certain orientations, certain angles where you get constructive interference between those. And so what you have in crystals are layers of atoms, planes that are generated by the regular repeating arrays of atoms. And what you can do is you can relate some of these parameters to the distance between those two planes. So the X-rays are going to go into the crystal at some angle, and you rotate the crystal around to sort of fix that angle. So theta is going to be the angle of incidence. And when you have constructive interference, it'll diffract off of that at the same angle. And then d here is the distance between the planes of atoms. Anytime, yep. And then the Bragg equation states that how do we relate all these things together? This is what they came up with. Again, I don't think you really need to know this equation or use it. I'm just giving you the background to understand how these structures are generated, so you don't think I'm just pulling it out of thin air. It's n lambda equals 2d sine theta, where n is an integer. And so essentially, you repeat this measurement for all different angles. You then generate a bunch of distances between all the atoms in the crystal, and you piece that information together to get the whole structure. So we're leaving out, there's a big gap there. I don't have the time to cover it in more detail, nor would you appreciate that if I tried to. But that's basically where this all comes from. You shine X-rays on crystals, you measure the angles of those X-ray diffracted beams relative to the crystal planes, and then you piece that information together to get the distance between the atoms. And that's how we sort of know then precisely where the atoms are located relative to each other in all directions. That's where this structural information comes from, but really what you have to be able to understand is how do we define the structures? What are the different possibilities? So we're going to be talking almost exclusively about cubic unicells, both for metal atoms, for metal substances, and for ionic compounds. So the really cubes are going to be the major one here. And so to understand how a little bit how this works, first you have to think about what are the different places in that cube that you can put the different metal atoms, or later on the ions that would be in ionic compounds. So the unit cell is defined by a sort of fictional cube that you then translate in all directions to get the lattice. Where can we put atoms within that cube? So one possibility is you can put an atom that's completely inside of the cube. So we call that the body center position, meaning that that atom is completely surrounded by the unit cell. It's all the way on the inside. It's not on the edge. So because it's completely inside the unit cell, it's not shared by other unit cells, and it counts as one whole atom. Because one of the ways that we're going to define these structures is going, and what we're going to sort of, how we're going to sort of characterize them relative to each other is partly that's going to be determined by the number of atoms that are in each unit cell. So if we want to count how many atoms are in one unit cell of the crystal, if the atom is completely inside of the unit cell, it counts as one full atom for that unit cell because it's not shared by other unit cells. But we have other possibilities that would involve atoms being on the borderline between two or more unit cells, and then thus they would be shared by those unit cells that are at that intersection or at that borderline. So one possibility is you can put an atom in the center of one of the faces of a cube. So cubes have 6 faces, 4 on the sides, 1 on the top, 1 on the bottom. And if you put an atom right in the middle of one of those faces, when you stack the unit cells together in all directions, that atom is going to be sandwiched in between 2 different unit cells. It's going to be in the face of one unit cell and the face of the one that's right next to it. So in this case, those face-centered atoms will be shared by 2 unit cells. And they're going to count as 1/2 of an atom when you're counting how many atoms will be in that individual unit cell. Another position which we won't really see until we talk about ionic compounds are the edge positions. So if you stack crystals together in all directions, they're going to have 4. If you stack cubes in all directions, you're going to have 4 cubes sharing each edge. So there'd be one next to it, one in front of it, and then one in that direction as well. So you'd have 4 cubes sharing an edge. So the edge positions are shared by 4 unit cells, and then count as 1/4 of an atom for that individual cell. We won't use the edge position until we start talking about ionic structures next time, but that is a possibility. And then finally, the last one is you can put atoms in the corner positions of the cube. So there are 8 corners in a cube, and each one can have an atom located at that corner. So when you stack the cubes together, there's going to be 8 cubes that share one corner. So you're going to have 4 on the bottom, 4 on the top for a total of 8. So a corner position is shared by 8 unit cells. A lot of this is just geometry at this point, stacking cubes together. So if you have cube-shaped blocks, you can stack them to help understand this a little bit better. And these count then as 1/8 of an atom for that unit cell. All right, so that's one of the things we have to be able to do is we have to be able to look at the structure, the unit cell, where are the atoms arranged in that cubic unit cell, and then count them up. The number of atoms in the unit cell does relate to some of the properties we'll talk about. All right, so let's go ahead and go through some of these in detail. We're going to have, at the very end, we'll have a summary that kind of gives you the essential information that you should definitely know, but I am going to go through them in a little bit more detail. 1, because I like this topic, and 2, because maybe I at least naively hope that this will help you understand it better, but you may disagree at the end. We'll see. All right, so the first one we're going to talk about is the simplest, and it's called simple cubic. So there's kind of 2 ways to visualize these structures. Probably the more useful one in most cases is to look at the cubic unit cell and understand where the atoms are placed in that unit cell for each of these different structures. But also you can think about them as being generated by taking layers of atoms and stacking them up in all directions. So if you want to generate a simple cubic structure, you start with one layer of atoms. That's shown like this, where all the rows are eclipsed. And so what that means is you have this top row here. The next row is directly below that. It's not slid over at all. The rows are directly on top of each other. So you form this type of layer here that has these little gaps in between, but all the atoms are touching along the sides. And then you just stack those layers directly on top of each other. Completely eclipsed. Again, no slipping, no of the layers, no offset or anything like that. So stack the layers directly on top of each other. So that's how you would generate a cubic structure, a simple cubic structure, by just stacking layers of atoms. All right. So that's the simple cubic structure. Now, again, the more useful way to visualize this is by looking at the actual. Yes, please. Go ahead. All right. So then you can look at just the cubic unit cell and where the atoms are arranged. So in a simple cubic structure, all you have is one atom at each corner of the unit cell. That's it. All right. So
Hold these to the hub, to the pump.
to canvas, I always do. Yes.
All right.
So then for the simple cubic structure, one atom in each corner, that's all there is. There's different ways of sort of picturing this. So this would be one unit cell. This would be an array of, I guess, about 8 different unit cells all stacked together. You take those cubes and you stack them to make the lattice. Another visualization of the unit cells to actually make the atoms fill up the entire space like they actually do, and show that they're arranged along the corners like this, and they're sort of just touching each other right along the sides of each cube. So there's different ways of visualizing this, but a cubic unit cell is simple cubic structure is just a cube with one atom in each corner. Nothing more difficult than that. One of the things that we can define then for each of these different structures we're going to cover is what percentage of the volume is occupied by the atoms. Because you'll notice in these different pictures we've drawn here, this one is showing the atoms as little tiny spheres, but even in the one down here, which fills all the available volume, you still have some pretty significant gaps between the atoms. So what percentage of that space is occupied? That sort of relates to the density of the crystal as well. So there's some important sort of correlations there. So how do we do that geometrically? And again, for the most of this stuff is probably beyond what you need to know, but some of these things are helpful to internalize. So if we have a simple cubic structure, if you look at one square face of that cube, so we're looking at basically this here, just one face of the cube with one atom in each corner. As we said, the atoms sort of touch along each side of the square. So the way that we define the size of a unit cell is by just, for cubic unit cells, it's just the length of each side. In a cubic structure, all the side lengths are identical. That's the definition of a cube. So we just call that A, the side length of the unit cell. If it was a more complicated unit cell that had different side lengths, it would be labeled as A, B, and C. But for a cubic cell, you just have one length because all the lengths are the same. It's A. And what you can see here is that if this is the atomic radius of the atom that's in that structure, the length of the side is equal to 2 times that radius. A equals 2R. And then if we want to define what percentage of the volume is occupied by the atoms, we have to also define the volume of the whole cube. The volume of a cube is A cubed. That's simple geometry, which is in this case equal to 2 times the radius cubed, or 8R cubed. The other thing we have to be able to do is count how many of those atoms or spheres are in the unit cell. That's where the counting rules that we learned a little bit ago come into play. So in a cubic cell, you have all 8 corners of the atoms, all 8 corners of the cube are occupied. Each corner counts as 1/8 of an atom because they're shared by 8 unit cells. So you have 8 corner atoms, all counting as 1/8. So in total, each unit cell just has one total atom in it. 8 1/8. Each corner counts as 1/8, and there's 8 of those, so a total of 1. The volume of the atoms themselves, or the spheres, if you're thinking about it more generally, the volume of a sphere is 4/3 pi r cubed. So you have one atom in the unit cell. The volume of that atom is 4/3 pi r cubed, where r again is the radius of the atom. So then if you want to define what is the packing efficiency, the percentage of the unit cell that is actually occupied by the atoms, you take the volume of the atoms, 4/3 pi r cubed, and you divide it by the volume of the cube, which is 8r cubed. Okay? So you just divide those two. So you take the volume of the spheres, which in this case would be atoms. We're talking about a chemical crystal, divided by the volume of the cube, multiplied by 100 to get it to a percentage. And so it's just going to be 4/3 pi r cubed for the volume of the sphere, divided by 8r cubed is the volume of the unit cell, multiplied by 100, comes out to pi over 6 times 100, which is 52.4%. All right, so in a simple cubic structure, just over half of the volume is occupied by the atoms that are in the unit cell. The rest is empty space. All right, so that's the first one we're going to cover. Again, we're going to summarize a lot of the important information later on, but in a simple cubic structure, you just have one atom in each corner. And with this derivation, you come up with a packing efficiency of 52.4%. So the next type of structure we're going to talk about is called body-centered cubic. So what you do in a body-centered cubic structure is you arrange the atoms on the 8 corners like we did before, and then you stuff one right in the middle of the cube. Now, in order to do that, we saw that in the simple cubic structure, all the atoms were touching along the sides. If you want to stuff a whole atom in the middle, you have to sort of separate them apart a little bit. So you open up the structure a little bit. So then if you think about it in terms of the layers, what you would do is you have to start with a layer of atoms that has a space in between. So to generate a body-centered cubic structure, you have to leave a space in between the atoms so you're able to fit one in the middle. Then you're going to put a second layer. For a metallic structure, the second layer is the same atom, identical to the first, but I'm just showing it in a different color so you can visualize it better. So this red layer here, you're going to stack on top of the gaps in between the first layer. So you're going to stack the second layer over the spaces in the first layer. And then the third layer is going to be exactly on top of the first layer. So you're going to just start repeating the process after that. So it's what we would call A-B stacking. You stack one layer, you stack the next layer, and the gaps between that first layer, and then you go and repeat that process over and over again. So we call it A-B stacking. So the third layer gets stacked right over the first. So what we say is that the third layer eclipses the first layer. Has a second layer in between it, but it's exactly on top of that first layer in terms of its location. I feel like for some people, the layer sort of diagrams don't really work so well. So I still think the more useful way is to look at the actual pictures that are shown here on the left. So in a body-centered cubic cell, these are all body-centered cubic, just different visualizations of it. But you can see that you have one atom in each corner, and then one more right in the center of the cube. And then this diagram down here shows the same thing with space filling. This time you have little gaps in between the atoms. You're stuffing a whole other atom in the middle. And that's what it looks like. And then this is what the lattice looks like if you take this cube and stack it up on itself in all directions. Okay, so that's what body-centered cubic looks like. Now we're going to do sort of the same geometric argument for body-centered cubic, but it's a little bit more complicated now. Because we can't just go through a face of the cube. Because if we look at a face of this cube here, as we said, there's a little bit of a gap between the two atoms that are occupying that face of the cube. So we can't easily define the length of one side in terms of the number of radii of the atoms because there's a gap in between them that's not accounted for. So the way we do it for a body-centered cube is we go through the cube diagonal. We go from one corner of the cube all the way to the opposite corner through the whole diagonal of the entire structure. And then from geometry, the length of that diagonal, this red line that I'm showing here, d squared is equal to a squared plus a squared plus a squared. It's kind of like the three-dimensional Pythagorean theorem in some sense. So the distance would be equal to a radical 3. So to go through the diagonal of a cube, the distance that we travel is equal to the length of a side, which is a, multiplied by the square root of 3. Okay, that's just geometry. Then what we also can notice is that as we go through that diagonal, we're going to pass through one of the corner atoms as we start in one corner, one radius of that corner atom. We're going to pass through the atom that's in the middle. Remember, in a body-centered cubic structure, there's one atom right in the middle here that we pass through. So we're going to go through both radii of that, 2r. And then we're going to have to pass through the other atom that's in the opposite corner up here. So as we go through that cube diagonal, we're going to go through 4 times the radius of the atom. One radius for each corner, plus the whole diameter of the center atom that we're passing through as we go through that diagonal. So what that means is that the diagonal length is equal to a times the square root of 3 as determined above, and it's also equal to 4 times the radius, because we're going through that diagonal, we pass through 4 atomic radii. So if we solve for a in terms of the radius, it's going to be equal to 4r over square root of 3. So in a simple cubic structure, a was just 2 times the radius. In a body-centered cubic structure, there's a different relationship. A is equal to 4r over radical 3. In terms of the number of atoms, number of spheres per unit cell, what we have are, in the body-centered cubic structure, we have all 8 corners are still occupied, so those each count as 1/8. But we also put that one atom in the center of the cube. Remember, the body-centered positions, the one that are completely enclosed by the unit cell, count as a whole atom for that unit cell. So that's the body-centered position. So there's a total of 2 atoms per unit cell when you're talking about body-centered cubic structure. One comes from the 8 corner atoms, one comes from the extra one that you're putting in the middle. All right. So then to get the volume of those atoms, it's going to be 2 total atoms. The volume of each is still 4/3 pi r cubed. So the volume of the atoms in this case is 8/3 pi r cubed. And then again, to get the packing efficiency, we take this volume, which is the volume of the atoms, divided by the volume of the cube, which is just a cubed. So we're going to have 8/3 pi r cubed for the volume of the atoms. The volume of the cube is 4r over radical 3. Whole thing cubed to get the volume of the cube. We can simplify this a little bit. It comes out to 8/3 pi over 4 over radical 3 cubed. And then if we put that into your calculator, multiply by 100, we get a packing efficiency of 68%. So a bit higher than we got for simple cubic. By forcing one atom into the center there, we're occupying more of that space. So the exact numbers may not be that important for us, but we should recognize that body-centered cubic is a more efficient packing of the spheres than simple cubic would be. All right, so that's going to be the numbers we get for body-centered cubic. All right, the very last cubic structure we're going to talk about is called face-centered cubic. This it looks a lot more complicated, but in reality, it's not too bad, as we'll see once we break it down. The other name for this you sometimes see is called cubic closest packed. Now that synonym kind of gives the game away, which ends up this being the most efficient way to pack spheres into a cube. There's no other way to do it that's more efficient than this. So the way that we generate this from layers of atoms is a little bit more difficult to visualize. But the way we start with the layer where all the atoms are as close together as possible. So instead of having the atoms directly on top of each other, we have one row of atoms, and then the next row is slipped so that it fits into the gap between those atoms. So to compare that to the first one, in simple cubic structures, all of these rows were directly on top of each other. For the closest packed structures, which includes this body-centered cubic, we take the second row and we kind of slide it a little bit over relative to the first one, so it fills in some of those gaps. So you start with what's called a close packed layer of spheres. And then in terms of how we stack it, so we're going to call the bottom layer, which is going to be in yellow here, the A layer. Different than the side length A, but it's abbreviated as A also. The second layer, which you can see here with these hollow spheres initially, we're going to put it right over those triangular gaps. So in these close packed layers, you have these little tiny triangular gaps between the atoms. So the second layer is going to go right on top of those triangular gaps. It's going to be, again, slid over a little bit. So we'll call that the B layer. And then the C layer is going to go over the triangular gaps in the B layer. It's not going to be exactly over the A layer yet. So the third layer, which is C, is going to be distinct, shown in green in these diagrams here. And then finally, it's going to be the fourth layer that ends up being identical to the first in terms of its placement. So what we have is an A layer, a B layer that's in the gaps of the A layer, a C layer that's in the gaps of the B layer, and then finally it repeats itself after that. So there's all these different ways of drawing it, and some of them may or may not be helpful, but what we call this is either ABC, or sometimes we'll see it labeled as ABCA packing. That means we have 3 stacks of layers before we start repeating the pattern over and over again. So it's a ABC packing. Again, the better way to visualize this is in terms of the cubic structure. So the name kind of gives it away. For face-centered cubic, we have a cube where we have all 8 corners have an atom in it. It's probably easy to see in this one down here. So all 8 corners have an atom, and also all 6 faces of the cube have an atom arranged in it as well. So there's 1 atom in each corner, and then 1 atom stuck into the face of each of those cubes. That's why I call it face-centered cubic. The way that sort of relates to the layers is shown here. So you have to kind of think of the layers along the diagonal of the cube. So this yellow layer A occupies that corner. The second A layer occupies the opposite corner, and then you have B and C sort of in between that along the diagonal of the cube. So those are kind of hard to visualize, but again, this picture here is probably the most useful one. All 8 corners plus all 6 faces have an atom in it. All right, so any questions so far on that one? So then to analyze this structure in more detail, we're going to look at one of these faces of the cube. So we're going to look at one cubic face, and what we see is that in that face you have an atom in each corner and one in the center. So then we're going to zoom in on that, and that's what it looks like. So in this structure here, this is the face of one cube, which has side lengths of A in all directions. So as we go through the diagonal of the cube now, sorry, not the diagonal of the cube, the diagonal of the face, we're going to go through 1 atomic radius. We're going to go through both atomic radii of that center atom, and then we have to go through the opposite corner as well. So you have gaps along each side as well, so you can't easily measure it like we did for the first one, but here using the diagonal equation, the diagonal of a square of one face of the cube is a squared plus a squared equals d squared. So d is equal to a square root of 2. So that's the length of the diagonal in terms of the side length A. That's from geometry. And then as we go through that diagonal, which has length of a radical 2, sorry, those should be r's, not a's. I'm sorry, messing this up. Those are all the atomic radii there as we go through that. So you go through 1 atomic radius on the corner, both atomic radii of the central atom in that face, and then you go through the radius of the other opposite corner. So you're going to go through 4 total radii, this time along the diagonal of the face. So A is equal to 4r over radical 2, or 2 radical 2r. So again, each of these different structures has a different relationship between the side length A and the radius of the atoms that make it up. So there's different values there. In terms of counting the number of spheres, oh, I messed this up totally. I'm putting everything in the wrong place. I'm sorry. I let the noise get to me. I blame the construction workers, even though it's really just me being totally spaced out. All right, I'm going to write everything else, but I'm going to put it in the right spot in the notes so it's not confusing anybody. Length of a diagonal. Length of a side, a radical 2 is the diagonal. That equals to 4 times the radius. So A is equal to 4r over square root of 2, or 2 radical 2r. And then the number of spheres per unit cell, fairly important one. So in this structure, we have all 8 corners are still occupied. There's no exceptions to that. You're always, in these cubic structures, going to have all 8 corners are occupied in all cases. And then for face-centered cubic, we also put 1 atom in each center of the face. A cube has 6 faces. So there's 6 of those positions. And the face-centered positions are shared by 2 adjacent unit cells. So they count as 1/2 each. So in the face-centered cubic unit cell, you have a total of 4 atoms per unit cell. 1 of those comes from the corner atoms, and then 3 from the faces. So that means the volume of those is going to be 4 times the volume of each sphere, which is 4 times 4/3 pi r cubed. And then finally, to get the packing efficiency, we take the volume of the spheres divided by the volume of the cube, which is just that number cubed over there. So 16 over 3 pi r cubed divided by 2 radical 2 r cubed times 100. Don't really need to simplify this anymore. We could simplify it a little bit, but numerically, it comes out to 74%. All right, so simple cubic was 52%. Body center cubic was 68%. Now we're up to 74% is the packing efficiency for face center cubic. That's as high as you can get in any of these structures. So face center cubic is the most efficient packing, which is why we call it cubic closest pack. The last one we're going to talk about, although not in as much detail, is called hexagonal close packed. So it turns out with hexagonal close packed, you have the same exact layers that you do for cubic close packed, but instead of doing ABC stacking, you do AB stacking. So after the first two layers, you start repeating again after that. So just a different way of stacking the layers, and it generates a different structure. So again, you have layer A down here, you stack layer B on top of that, and then you start repeating it right after that. So it's just alternating pattern of only two layers this time. In terms of the number of atoms in a unit cell, this one's a little bit harder to deal with, but I'll give it to you anyway. So number of atoms, what you have in this structure here are, because they're made up of hexagons, they're sort of each edge is shared by 6 hexagons. So you have 12 atoms along the edges that each count as 1/6. This one you don't have to worry about in as much detail. I'm giving you the details just for your own purposes. You have the so those are the 12 along the edges. You have 3 that are in the center, completely enclosed by the hexagon. That would be these blue ones here. And then these ones on the top of the center of each one are going to be shared by 2 adjacent cells, so they count as a half each. So in a hexagonal unit cell, you'd have 6 total atoms. The only thing you need to know about the hexagonal cell, we're not going to talk about it in any more detail than this. Know that it's generated by AB stacking instead of ABC stacking. So it's identical to cubic, except that it's just a different way of stacking the layers. So we call this AB, or sometimes you'll see it called ABA stacking, meaning that you have just 2 repeating patterns, not 3 in this case, 2 layers that repeat themselves. And the other thing that's important to know is that the packing efficiency for hexagonal, which we're not going to derive, is exactly the same as cubic close packed. So you don't have to know all the details of the hexagonal structure or be able to visualize it as well, because it is more complicated than cubic. Because the unit cell no longer has nice 90-degree angles, no longer has identical side lengths either. But the packing efficiency is exactly the same. So if you know that it's the same packing efficiency, and the only difference is just how you stack the layers, that's really the depth you need to know for hexagonal. The other thing that we're going to define for these unit cells, and it also comes into play when we start talking about ionic structures as well, is called the coordination number. The coordination number is the number of nearest neighbors that each atom has. Basically, the number of other atoms that are touching it. Number of nearest neighbors. One of these days I'll learn how to write. So in other words, it's the number of other atoms an atom is touching. And what shouldn't be too surprising at the outset of this is that we talked about the different packing efficiencies that each of these has, and essentially the coordination number sort of scales with packing efficiency. The higher the coordination number, the higher the packing efficiency, because if you want to pack them closer together, you have to have more atoms sort of touching each other. So we can define this for these different structures in different ways. So if you look at the simple cubic structure, let's focus on this atom right here marked with an X. So in the same layer as that atom, you have 4 other atoms that are touching it, one on each side like that. So those 4 would all be nearest neighbors and count towards the coordination number. And then you also have, if you think about the layers being stacked on top of each other, you have one above that's in the layer on top of it, and one below that's in the layer below it that are also touching that atom. So you have 2 others from the above and below layers. So one above and one below. So that's a total of 6 atoms that are touching each other atom in the structure, meaning the coordination number for this one, abbreviated as Cn, is equal to 6. All right. So for simple cubic, you have a coordination number of 6. Each atom has 6 nearest neighbors that is touching. If we go to body-centered cubic, in these cubic structures, all of the positions are equivalent. So when we stack them out and make the lattice, every single atom is equivalent to each other. There's only one sort of environment for each of those. So for body-centered cubic, we just focus on the atom that's right here in the center of the cube, the one that we put in the middle there. What you can see is that it's going to be touching or bordering all of the atoms that are in the corners. There's 8 corners in a cube. 1, 2, 3, 4, 5, 6, 7, 8. So in the body-centered cubic structure, each atom has 8 nearest neighbors, so the coordination number is 8. We said as the packing efficiency gets higher, so does the coordination number. So simple cubic is 6, body-centered is 8. The one that's a little bit harder to visualize, but we can still do it if we think about the layers and the structures, is going to be for face-centered cubic. I used to have a better picture of that. I don't know where it went. But anyway, what you would have is if we focus on this atom here, which I'll mark with an X, in the same layer as that atom, you have now 6 nearest neighbors. 1, 2, 3, 4, 5, and 6. And then what you also have in the layer below that atom is going to be touching the 3 that it's sitting on top of. So remember that each layer sits on top of one of the triangular gaps in the layer below it. So this atom marked in X is going to have those 3 atoms in the bottom layer, 7, 8, and 9 that are touching it. Those are 3 in the yellow layer. And then you're going to have another layer on top of that. So this is atom X here. And then above that, in these green ones, you're going to have 10, 11, 12 in the layer that's above it. So again, whether you fully follow that or not, the coordination number for the close packed structures, either face-centered cubic or hexagonal, you can add that in as well, they would have coordination numbers of 12. 6 atoms that are in the same layer, 3 above, 3 below, that are all touching that same atom. All right, so you have the coordination number increases as you go through and do and increase the packing efficiency as well. Now, as I promised at the beginning, I'm going to sort of end this with a table that summarizes what I think is the most important information. If you know everything in the table, you'll probably be fine for most of the exam questions. Some of the geometric arguments that I presented earlier, especially the relative length of each side, might be helpful to know as well. But mostly it's this information here that's going to get you through the problems in this course, and of course understanding the concepts behind them. All right, so for simple cubic structure, there's a synonym for it that we haven't given yet called primitive cubic. So whether it's called simple cubic or primitive cubic, those mean the same thing. In a simple cubic structure, you just have all 8 atoms, all 8 corners occupied with atoms and nothing else. So there's a total of 1 atom per unit cell, 8 corners that count as 1/8 each. The coordination number for that ended up being 6, as we just saw, and the packing efficiency was just over 52%. Okay. Body-centered cubic can be abbreviated as BCC. So it's not really a different name. It's just an abbreviation for it. The number of atoms per unit cell was 2 because you have 8 corners, which count as 1 total atom, plus 1 more in the middle, so a total of 2. Coordination number was 8. If you focus on each of those center atoms there, they have 8 corners that are surrounding them, so that's a total of 8. And a packing efficiency we came up with was 68%, so a bit higher. Face-centered cubic was the most recent cubic structure we covered. Again, abbreviations more so than anything else. FCC for face-centered cubic, or CCP for cubic close packed. not Chinese Communist Party, but cubic close packed in this case. So CCP, the number of atoms per unit cell was 4 because you had 8 in the corners that counted as 1, 6 faces that each counted as a half, so a total of 4 when you add that all up, and a coordination number of 12, best visualized by considering the layers, which you have 6 atoms in the layer, 3 above and 3 below, that all border it. And the packing efficiency was the highest at 74%. The hexagonal close packed structure, HCP, is generated from the same types of layers as face center cubic, just stacked in a different way. They have 6 atoms per unit cell. That one is not as important because there's different ways of defining that cell. But the coordination number and the packing efficiency for hexagonal are identical. So that's the most important things to know about that one. So those are the different metallic structure types we have. And that's really all we're going to cover in this course. So if you know those 4, especially the 3 cubic ones, which come up the most, you should be fine. What we're going to talk about next time are ionic structures and some other types of compounds as well. But for ionic structures, we start with this basic framework here, and then we're going to fit other ions into the gaps in the structure, and that's how we're going to generate those. So there'll be a little bit more, but a lot of it is based off of the same ideas. So we'll pick that up on Tuesday of next week.